Through the course of this year in geometry, we're certainly going to come across literal equations. So your goal in literal equations is not to solve it in the traditional sense. You're not going to get a numerical answer. Instead, what's happening here is you have some sort of equation, has a handful of variables in it, and you're going to be using some properties of algebra to just simply rearrange that equation so it's still an equivalent equation. So right now we have the perimeter equation for a rectangle. Perimeter is equal to 2 times the sum of the length plus the width. But let's say, for example, I wanted to rearrange this so that I have L equals, or let's say W equals, all by itself. Right now, how we usually phrase this is that we say that P here, perimeter, is in terms of L and W. In other words, we need to know what the length and the width are in order to calculate the perimeter. But maybe I want the width in terms of its perimeter and its length. What that simply means is that I need to solve this equation for W. So what would I do first? If I'm trying to get W all by itself, notice that it has an L beside it and it has a 2 beside it. I want to get rid of this 2 first. The 2 is being multiplied by that set of parentheses, so I'm going to divide both sides by 2, and here's what my new equation looks like. P divided by 2, half of the perimeter essentially, is equal to length plus width. Okay, so again, going with the same example, if I wanted to just solve that for W, I have this L that's getting in the way. This L is being added to the W, so to get rid of it, to get it onto the other side, I'm going to subtract it to the other side. And so I have perimeter over 2 minus the length is equal to W. Of course, if we wanted to, if we wanted to solve it for W, we usually have that on the left-hand side, so I'm going to use symmetric property, just basically flip that thing over. Okay, and so now I can see that W is equal to P over 2 minus L. In order to calculate the width, I need to know the perimeter and the length. Our width is in terms of perimeter and length. All right, so let's give one of these a try where we're working at it from scratch. It's not all animated like this one was. We're actually writing out the steps. So solve the equation 3h is equal to m plus 1/7 rg, and we're solving that thing for g. Okay, let's come over here so I have some working space. What I'm going to do is I'm going to highlight, this is a strategy I would suggest to you. I'm looking for G. That's the thing I'm trying to isolate. So let's think through this process of what I'm going to have to do. So look at all the stuff that surrounds G. I want to keep G where it's at and get rid of everything else that surrounds it. I have this M, and I also have this 1/7 times R that's being multiplied times here. I got to ask myself, what am I going to get rid of first? Am I going to get rid of this M, or am I going to get rid of this 1/7 R? Well, if I think it's the stuff that surrounds the G that's being multiplied times the G, if I multiply both sides by 7, that might be something that could work. I mean, we have already talked about how, if we have fractions, we can make that thing simpler by multiplying by 7. I think that might be a pretty good strategy. So here, let's go ahead and give it a try. I'm going to copy my equation down again. What happened there? I don't even know. Okay, m plus 1/7 r g. So if I multiply both sides of this by 7, and I'm doing that because it's the only denominator that I have here, and I'll need to distribute the 7 to every single term here. So 7 times 3h gives me a 21h. I have to do it on the right side also. 7 times the m gives me a 7m. And then here was the whole entire reason why I chose this. If I multiply 7 times 1/7, I get 1. These things are reciprocals of each other. They're multiplicative inverses. I can also think of this as 7 over 1, and whenever I do top times top and bottom times bottom, I get 7 divided by 7, which of course is equal to 1. All right, so that means that that fraction disappears, and I'm left with a capital R and then G. Okay, so we're one step closer to getting G all by itself. So now I have this 7m that's over here, and I have this r that's right beside the g. What am I going to get rid of next? Should I move the 7m or should I move the r? So some people think that I need to, like it's right next to the g, I need to get rid of that r. If I get rid of that r, I think that it complicates the problem, because what it's going to do is going to create a fraction on this one, and it's going to create a fraction on this one. I want to first get rid of the 7m. Essentially, I kind of want to think of like the order of operations whenever I'm solving equations. I kind of work that process backwards. And so I want to do this adding and subtracting of these terms over here before I do the multiplication or division to get rid of the r. And I know you might be thinking, well, what about that 7 that was there? We didn't have to multiply by that 7, but it certainly did make my equation easier to work with because now there's no fractions in it, right? So what I'm going to do is subtract this 7m to the other side of the equation. Okay, there's no common terms or like terms on the left-hand side, so I'm just going to have to list those out. 21m minus 21h, how about, minus 7m is equal to, these cancel out of course, is equal to rg. And now I only have one thing that I have to get rid of. This r is being multiplied times g, so to get rid of it, to get it to the other side, I'm going to divide both sides by r. Okay, once again, the r has nothing in common. There's no like terms over here, so there's no simplification that is going to happen. So I'm just going to rewrite that problem, that side of the equation, 21h minus 7m over r. Of course, on the right-hand side, the r's will cancel, and I'm just left with g. So I'm good to go. I might flip this around and make it so that g comes first. It's on the left-hand side, so g is equal to 21. Try that again, 21h minus 7m over r. I think that was supposed to be a capital M. Didn't look very capital. And there we have our answer, our final answer. Let's say this is a multiple choice type of situation. And I look at my answer choices and I don't see this as an answer choice. How else could this be written? Well, one of the things that could happen on this one is that maybe whoever wrote this question or wrote the test that this is on divides that r into both of these pieces. It's essentially the distributive property, but I'm using division with it. I got to divide it into that term and I have to divide it into the other term as well. So it's possible that the answer choice on a multiple choice would look like 21h over r minus 7m over r. Maybe it looks like that. I look for that answer choice, maybe it's not on there either. Is there anything else that we could have done to it? Maybe it's still one complete fraction, but the top is a little bit different. Well, there is one thing that could happen on the top, and that is the top has a common factor of 7. One of the other parts of this lesson is about factoring, and this is one of the things that you can do when you factor. If something has a common factor, you pull it out, and it's basically the reverse of the distributive property. Common factor of 7 would look like this. I'd pull out 7, open up my parentheses, and now I divide both of these terms by 7. 21h divided by 7 gives me 3 h's. Negative 7m divided by 7 gives me negative m over r. So possibly in a multiple choice scenario, it could look like a whole bunch of different things. And I even tell my calculus students, after we're done with our calculus, it's a multiple choice question. Now it's time for me to use some sort of algebra to make my answer match up with theirs. Okay, so again, just kind of a recap on these literal equations. I am just using some algebra to skillfully rearrange my variables to solve for a particular one, to isolate it in some kind of way.